Today we are looking at a true technology giant in Europe, which is called Bosch. Bosch has a unit that is busy with building quantum sensors, and if you want to learn more about what this is all about, what sensors they are working on and what the applications of those are, then make sure to stay tuned for today's video because we are diving into Bosch quantum sensing. And with that, let's have a look right onto their website. So here we are on the Bosch quantum sensing website. We see the Bosch logo. So Bosch, if you might not know them, they're one of the biggest suppliers in the automotive manufacturing industry within Germany. And they are, of course, active globally with a extremely, let's say, worldwide workforce and also production capabilities worldwide. Here we are on Bosch quantum sensing, so that's kind of a subunit. And they say create beyond possible. So we already see this is very application focused here. We see the applications, or let's say typical business applications of today running here on the site in the video. There's some call to action to learn about the application fields and the technology. But before we do that, let's quickly check out what else we can find on this initial page. It says quantum technology will be a game changer in many areas, truly an invented for life technology, says Stefan Hartung, chairman of the board of management of Robert Bosch GmbH. There's also a video, we are not going to watch that. Here again, create beyond possible. Following this guiding principle, we at Bosch Quantum Sensing are shaping the future, united by our mission to create game-changing solutions that improve the quality of life for everybody worldwide. Building on over 10 years of foundational research in quantum sensing, our cutting-edge sensor technology harnesses the principles of quantum physics to deliver measurements with unprecedented accuracy in portable device. Compact, robust, and user-friendly, our magnetic quantum sensors represent a true quantum leap across various application fields, from medical technology and consumer goods to navigation, resource exploration, and process optimization. All under the roof of a company uniquely capable of transforming technologies from the experimental stage to industrial application, the Bosch Group. Let's quickly see where they push the boundaries. So it's research, excellence, startup environment, exceptional team, user centricity, global network, and leaving an impact. Here again, we see the different application fields. So we see there's a medical application, consumer goods, process improvements, and then navigation and exploration. Want to partner up? Join us in pioneering the next generation of precise technology at Bosch Quantum Sensing. We are seeking innovative partners in all possible application fields to revolutionize industry standards together. And there's a call to action to contact them or to learn more, I guess, by the newsletter. Finally, we see some news in the news section down here. It says Bosch establishes company with the synthetic diamond solutions provider Element 6, quantum sensing technology unlocking new dimensions. And then there's also this one here from end of 2025. Bosch is again hosting partner of Quantum Effects 2025. I'm recording this beginning of 2026, so I guess this is pretty much up to date here. Now let's quickly check out the technology first to see what types of sensors they are working on, because we know there are like different sensors. We have seen the SNSPDs, so the basically superconducting single photon detectors. If you haven't heard about them yet, make sure to check out our playlist on the YouTube channel about the hidden quantum champions. There you can find many more videos like this one here, talking about the technologies, companies, and everything related to the field of quantum technology. But now let's see what Bosch is doing. So there's nothing more exciting for an engineer than setting foot in uncharted territory. That means driving forward the development of quantum sensor technology and tapping into brand new markets and applications, says Frederick Schaal, CTO of Bosch Quantum Sensing. So our technology, small and powerful, a new era of quantum sensing. Our cutting-edge magnetic field quantum sensing technology harnesses the power of quantum physics to enable measurements with unmatched precision. Combining extraordinary sensitivity with a compact form factor, our sensors are destined to transform a wide range of applications across numerous industries. Magnetic field quantum sensors surpass the capabilities of conventional sensors by offering wider measurement range, higher sensitivity, and higher spatial resolution, all while being remarkably robust, non-invasive, and easy to set up. This unique combination makes our technology ideal for applications requiring superior precision and minimal disruption. Moreover, our magnetic field quantum sensors hold significant advantages over earlier quantum sensing techniques like SQUIDs, superconducting quantum interference device, vapor cells, or optical traps. While these methods have proven effective, they often require large, complex setups with limited flexibility. In contrast, our magnetic field quantum sensors offer a similar performance in a much smaller, more versatile, and cost-effective package, unlocking new possibilities for sensing applications that were previously unattainable. Okay, so let's take a quick step back from that. What is the technology that we have here? So we are talking about synthetic diamonds, probably NV centers, as far as I understand. So these are usually diamonds, like the crystals that you know from your jewelry probably. And within there is a little, so they're very pure. It's just carbon from an atomic point of view. But they put in usually an NV center in there, so like a nitrogen vacancy, so a nitrogen atom. And this then behaves like a single nitrogen atom in nature, more or less, or like an ion that is trapped in a vacuum trap. But with the difference that you don't need the vacuum trap, it's just within the crystal. And now you can optically read out this ion by using light and a detector and looking at like how the response of that ion is depending on which state it is in or which polarization it has. And then you can use magnetic fields to manipulate that. And this is basically how you reach this very, very high resolution or high sensitivity, because you are basically talking with, or you are reading out a single atom and a single atom's energy levels, which are quantized, so the lowest possible energy level scales that you have available in nature, more or less. So that's the idea. There are other technologies mentioned here, like the SQUIDs. I've also been, during my studies, working with a SQUID in the lab for once. It is extremely exciting because you're using all these fancy equipment, superconductors, superconducting magnets to turn on the magnetic field. Maybe you don't even need them because they're extremely sensitive. You need liquid helium to cool them down. There are also some that work, I think, under higher temperature conditions, but still, I mean, you need a lot of fancy equipment. This is definitely not something that you will put in your smartphone at some point. While for these NV centers, they can operate at room temperature. They're a little bit easier to handle. Then, of course, here it says great performance and small package. Our sensor USPs, so extremely sensitive, small in size, higher spatial resolution, wide measuring range. Then we see exceptionally comprehensive and highly robust. So how does the sensor work? Let's quickly see how they explain it. Our quantum sensing magnometer uses a diamond as the core sensing element. This diamond has nitrogen atoms added as defect, known as NV centers. These nitrogen vacancy centers are remarkable as the extra nitrogen atom provide additional electrons acting as tiny magnetic field sensing elements. These NV centers change the diamond's optical and electronic properties. When green laser light is shown on the diamond through an optical focusing unit, it excites the electrons within the NV centers to a higher energy level. As the electrons return to their ground state, they emit photons visible as red light, which is separated through an optical filter and then detected by a photodiode. The key phenomenon, however, is that the energy levels of the NV senders are highly sensitive to changes in the external magnetic field, which enables them to be used as a quantum based on the Zeeman, as a sensor, I guess, based on the Zeeman effect. These quantum states are accessible via microwave radiation. When electrons occupy these levels and are excited by the green laser light, they no longer decay by emitting red photons, but instead remain dark. By varying the frequency of the microwave radiation and observing changes in the intensity of the emitted red light, we can precisely determine the strength of the external magnetic field. And now to the applications. So on the medical side, the applications that are mentioned here are magnetocardiograms and control of prosthesis. So MCG is, I think, kind of a known thing, right? So you are measuring the heart more or less, but in a very non-invasive way, I guess, because it's using the magnetic field rather than like attaching something to your body and reading, let's say, the electric signals right away. So here it says user-friendly operation and robust performance, extremely sensitive and accurate. So what else do we have here? Contactless and robust. So unlike ECGs, which require electrodes to be attached to the skin, MCGs can be performed without direct skin contact, even through clothing, and with virtually no setup time. This enhances efficiency, saves valuable time, and reduces the risk of skin irritation, discomfort, and issues related to poor electrode contact, which are often caused by sweat or patient movement. Thanks to their superior measuring technology, MCGs ensure accurate readings regardless of sensor alignment or exact position, offering great potential to enhance diagnostic precision and increase the likelihood of early detection. And that's the one side. The other side is on the prosthesis. So basically, I guess reading out the neural activity within the arm to kind of trigger motions in this prosthesis here. So the unique properties of magnetic field quantum sensors also create intriguing new possibilities in assistive technologies. Our non-invasive measuring method will be able to detect the stable magnetic signals of muscle contraction, not only from the upper muscle layers but also from deeper layers. As current myoelectronic sensors face limitations in accessing these signals, our sensors have the potential to pave the way for more refined natural control of prosthesis. As we advance our technology, we aim to develop brain-computer interfaces, BCIs, that intercept brain-generated magnetic fields, offering unprecedented control over prosthetic devices. This is for the medical side. Let's quickly also check out on the consumer goods. So here it says brain-computer interface and hard monitoring of drivers. I guess drivers as in car drivers. Then we see here on the process side non-destructive testing and battery control. So basically optimization of tests in the field. So non-destructive testing is vital to a wide field of industries, particularly when product safety and reliability are crucial. Aircraft components, train tracks, oil and gas pipelines, lithium batteries, and many other applications rely on maintaining material integrity, which can only be ensured through regular non-destructive testing. While several well-established NTD technologies are widely used today, our magnetic field sensor quantum technology promises significant advantages in terms of dynamic range and penetration depth while ensuring material integrity. And I mean, you've probably heard about it, but like you can also use ultrasonic, for example, to check for for cracks within this material here. This is something that has to be done on a regular basis on these kind of setups like pipelines to make sure that the material is still intact and that there's no risk of them kind of bursting apart. Same for batteries. You don't want the battery in your car to explode, so you kind of need to monitor its properties. There are also safety measures taken that if a cell kind of explodes, it doesn't explode the whole battery, right? And you also need to kind of check these things. You want to check in the process as well if the battery is correctly assembled, if everything is kind of working as intended, and therefore you need this. You need new technology or new methods to make sure that this is working at scale in a very reliable way. Then you see airplane navigation. Airplanes today have, of course, already some way to navigate. There's, of course, one way for the pilot to just look outside the window and see where you are. But if you're above the clouds, that usually doesn't help you much. Then you also have a magnetometer in the aircraft. So a gyroscope within the aircraft, and you can of course also measure the magnetic field. And there's GPS, and I guess GPS is nowadays the let's say preferred method. Now, harnessing the Earth's magnetic field, our magnetic field quantum sensor measures magnetic field with exceptional sensitivity and precision, including the magnetic field of the Earth. This unlocks new opportunities in both air navigation and mineral exploration. In airplane navigation, our sensors promise to provide an interface proof complete to GPS, ensuring a reliable positioning even in environments vulnerable to signal interruption. In exploration, by detecting even the slightest variation in Earth's magnetic field, they will enable the identification of potential mineral resources in Earth's crusts from above ground, airborne, and even underwater. Why that? Because if you think about the Earth magnetic field, you know that there is like a metallic core within the Earth that is producing this magnetic field, and it usually we say it comes out. So the magnetic field lines, you see that I think on this little symbol here as well. The magnetic field lines are leaving the Earth, and here on this simulation here on the poles, and then kind of entering on the other side. And this is the Earth magnetic field that protects us from the cosmic radiation. There has been some changes also observed of the magnetic field, so the poles are kind of changing their position over time. But then this magnetic field is everywhere present, and since it's such a big magnet, it is also kind of, let's say, in a first order, very, very constant, very stable, depending on where on this field lines you are. But then if you're looking at the precise measurements, those will actually also depend a little bit on what is happening in the Earth crust, which is basically what we are seeing, where our oceans are sitting, where our land is being at, right? This very thin sheet on top of the Earth's core. And this actually also serves as an amplifier, or maybe also not as an amplifier of the magnetic field. So consider or imagine you have a lot of metal, a lot of iron, for example, within the Earth crust. Then this iron can work like a little magnet. You might know that from school with the experiments. You take a little nail, and then you take a magnet and you rub it along the nail, and after some time it becomes magnetic. And the same is true for these minerals that are sitting in Earth crust. So some of those compounds, they, for example, amplify the magnetic field. Other ones are damping the magnetic field. And we know the different properties of the different compounds that are naturally occurring in Earth's crust. And thereby we can kind of make an estimation whether there is nothing here, whether there is maybe gas only in there, or if there is like metals below the field. And that's basically how you explore or how you search first order for these mines. And then I think that's about it on this one here. I don't want to go into the whole detail of this. And that's, I think, everything that we wanted to look at today. But all of this just to say, so I think there are already some applications where quantum sensing is becoming crucial, where it is being explored in real type of applications. Some of them are pretty niche, like exploration of, I don't know, mines and minefields is probably not something that every one of us gets in touch with. But if you think about these hard measurements, this is something that at some point in time everybody of us might get in touch with. So these are huge mass markets, very interesting. And the quantum sensors, they are actually already at a point where this is now being explored. So possibly we will see at some point some of these sensors in our day-to-day life. What an exciting thought to see quantum physics kind of helping us in our day-to-day life. With that, I also want to close already today's video. As always, make sure to stay hydrated and see you in the next one. Bye bye.